Welcome back to my channel. Today we are looking at LR circuits. An LR circuit is a circuit that contains an inductor and a resistor. Here is an example of an LR circuit. We have a battery of EMF E, a switch S, inductor L, and resistor R. They are all connected in series. When the switch S is closed, the current starts to increase, and the inductor responds in a very interesting manner. And then when the switch is opened, the current starts to decrease. And again, the inductor responds in a very interesting and different manner. Today we will look at the response of the inductor to changes in current. Joining me today is Giselle the Gazelle. Also joining me today is Isabel. Thank you very much. Let's begin by looking at inductors. An inductor is simply a coil of wire, like this. When a current runs through the wire, it sets up a magnetic field inside the coil. And that field produces a magnetic flux, phi m. And that magnetic flux is proportional to the current. And we have this, phi m equals L times I. L is called the self-inductance of the coil, or in this presentation I will refer to it as the inductance of the coil, and L is a constant. Now let's look at inductors and Faraday's law. Faraday's law. An EMF E is induced in a coil of wire when the magnetic flux phi m through the coil changes. I will refer to that EMF in this presentation as VL for the voltage induced across the inductor. Here's the relationship. VL equals E equals d phi m by dt. Now, we just saw that phi m equals L times I. So let's differentiate this expression. d phi m equals L di by dt. Of course, L is a constant. So what we see here is that a changing current produces a changing magnetic flux. Now, let's put this expression for d phi m by dt into here, and then we can write VL as L di by dt. So when the current through an inductor changes, a voltage VL is induced across the inductor. Now let's look at inductors and Lenz's law. Lenz's law. The induced EMF is in the direction which opposes the change in current that produced it. Let's look at an example. Here we have current flowing to the right, and this current is increasing. So the inductor is going to respond like this. It's going to have an EMF which is in the direction opposite to that of the current. This will oppose the change in the current. So this end will be the positive end of the induced EMF, and this end will be the negative end. So that's going to oppose an increase in the current. Let's look at another example. Here we have the current going to the right, but now it is decreasing. How will the inductor respond? It will act like an EMF in the direction of the current to oppose the change in current. So now this side is the positive terminal, and this side is the negative terminal. This will try to prevent the flow of current which is decreasing. It will try to prevent the decrease in current through the inductor. Let's look what happens when we close the switch in this LR circuit. So we've got an EMF, the battery of EMF E, switch S, inductor L, and resistor R all connected in series. So let's close the switch. When we close the switch, current starts to flow. It flows from the positive terminal of the battery to the negative terminal of the battery. So it flows in the direction shown here. It goes up through the inductor. Now, the current starts at 0, and then it starts to increase. Now, the inductor needs to oppose that change in current. So di by dt is greater than 0. And so the inductor is going to act like an EMF, with the positive terminal at the bottom and the negative terminal at the top. This will oppose the increase in current up through the inductor. And if we measure the voltage across the inductor with the positive voltage here, positive terminal of the voltmeter here, negative terminal up here, the measured voltage, VL, is L di by dt, and that's going to be a positive number. Now let's apply Kirchhoff's loop rule to this circuit. Let's start at the battery and go around like this. So we've got a voltage of increase of E through the battery, then a voltage drop through the inductor, and then a voltage drop through the resistor. So E minus VL minus IR equals 0. Now let's put in what VL is. All right, VL is L di by dt. So put that into here. And that will give us a differential equation. We get E minus L di by dt minus IR equals 0. Let's solve this differential equation. How do we do it? We need to use separation of variables. We need to put the i's on one side of the equation and the t's on the other side. So let's rearrange it like this. We get L di by dt equals E minus IR. Now, let's divide by E minus IR and multiply by dt, and we get this. Now we have all the i's on one side and all the t's on the other side. The variables have been separated. Next step is to integrate. L is a constant, so I can take it out of the integral. So this integral on the right is easy, it's just t. This integral is a little bit more complicated. We need to use a u substitution. U equals E minus IR. Differentiate this. E is a constant, so du equals negative di times r. So du is negative r di. So let's put this du into here and put the u into here, and this is what we get. So di is du over negative r. So du over negative r. We have the L, which we had before, and then E minus IR is just u. So we have this for the left side, and that equals integral of dt. Well, this integral is easy to solve now. It's just ln u. So we get this. ln u equals negative r over lt plus c1, where c1 is a constant. Let's continue. We don't want ln u, we want u by itself. So let's go e to both sides. E to the lmu equals e to negative r over lt plus c1. I can rewrite this exponential into two factors, like this. E to the c1 times e to the negative r over lt. E to the c1 is a constant, which we can just call c2. And e to the ln u is just u. So we get this. U equals c2 e to negative r over lt. Now let's put in what u is. U is E minus IR. So we get this. E minus IR equals C2E to negative R over LT. We need to find that constant C2. How do we do that? We need some initial condition. What is one of our initial conditions? Well, when t equals 0, the current was 0. So let's put these two things into this equation. We'll put I equals 0 into here, and t equals 0 into here. This is what we get. E minus 0r equals C2 e to the negative r over L 0. This term is just going to be 0. E to the 0 is just 1. So we get E equals C2. So we get this. E minus IR equals E times e to the negative r over LT. Let's solve this thing for I. Let's put the IR on one side. We get this. Now let's take out the common factor of E and divide by R to get our final result for I. I equals E over R times 1 minus e to the negative r over L times t. Let's plot the current versus the time. So here we have the current on the vertical axis and time on the horizontal axis. Here's what we get. As you can see, the current starts at 0 and then reaches a maximum value equal to E over R after a long time. Calculation of voltages. Resistor voltage. We know what I is. This is what I is. That's the current through the resistor. VR is just I times R. So take our current, multiply by R, and you can see that the R's are going to cancel out. So VR is this. It's E times 1 minus e to the negative r over LT. Now let's look at the inductor voltage. There's two ways we can do this. First, we can use Kirchhoff's loop rule. So let's do a Kirchhoff's loop. We'll start here at the battery and go around like this. So we're going to start with E, then voltage drop across the inductor, and then the voltage drop across the resistor, and that's going to equal 0. So we get E minus VL minus E times 1 minus e to the negative r over LT equals 0. Note here, this E and this E here cancel out. And so we get VL is E times e to the negative r over LT. Second method, we can use this expression. VL is L times di by dt. So we have to differentiate I with respect to t. First of all, we have the L. We have the constant E over R. So that L times E over R, we have that. Then we got a negative sign here. Well, derivative of 1 is just 0. Then we have a negative sign, so we have the negative here. Then we need to do the chain rule. We need to differentiate this exponent with respect to negative r over LT. That gives us e to the negative r over LT. Then differentiate negative r over LT with respect to t, giving us negative r over L. So L's cancel out. R's cancel out. And negative times the negative is a positive, and so we get e times e to the negative r over LT. It's the same as this. They're both the same, which is what we expect, of course. It is the inductor voltage. Let's look at a graph of voltage versus time. Here's voltage on the vertical axis, time on the horizontal axis. Let's see what we get. So blue is the resistor voltage, red is the inductor voltage. Inductor voltage starts at E. There was a voltage spike. It went from 0 up to E when the switch was first closed. And then it decreased exponentially to 0. The resistor, on the other hand, started at 0 voltage, and then it increased to the EMF of the battery, E. So initially, when t equals 0, the entire battery voltage was across the inductor, and none was across the resistor. After a long time, all the battery voltage was across the resistor, and there was no voltage across the inductor. Time constant. The voltage across the inductor after closing the switch is this. We can write this as E times e to the negative t over tau, where tau is called the time constant, and it equals to L over R. Let's see what happens when we change the time by the time constant. So when t equals 0, VL is just E, right? Put 0 here, e to the 0 is 1, so VL equals E. Now let's look at when t equals tau, the time constant. VL is E times e to the negative tau over tau, which is the EMF over E. So when the time changed from 0 to tau, the voltage decreased by a factor of E. Now look at t equals 2 tau. VL equals the EMF times e to the negative 2 tau over tau, which is EMF over E squared. So from time tau to 2 tau, the voltage across the inductor decreased by the factor of E. So when the time is increased by tau, the voltage is decreased by 1 over E. This factor, e to the negative t over tau, for different values of t, we have these things. It starts at 1, and then it decreases to 0 as time increases. Let's look at the graph of voltage versus time. Now I have EMF on the vertical axis and tau on the horizontal axis. And we can see here that after about time of 5 tau, the voltage has pretty much gone to 0 and remains 0 after that. So a time of 5 tau is enough to reach the steady state conditions. When t equals tau, the voltage is EMF over E. When t is 2 tau, the voltage is EMF over E squared. When the time increases by tau, the voltage gets closer to 0 by a factor of 1 over E. So at 3 tau, the voltage is E over the EMF over E cubed. Now let's look at the voltage across the resistor. It is the EMF times this factor, 1 minus e to the negative t over tau. Let's look at that factor, 1 minus e to the negative t over tau, for different values of t, from 0 up to 6 tau. Starts at 0 and then gets closer and closer to 1. Here's what it looks like. Starts at 0, gets closer to 1. We can see again, after about 5 tau, it's pretty much equal to 1. Or it's equal to the EMF E, but the factor is equal to 1. So when t equals tau, this is what the voltage is. EMF times this factor, 1 minus 1 over E. So how far is it from the final value of voltage? It is a distance of EMF over E away from the final value. Let's look at a time of 2t. It is at E times 1 minus 1 over E squared. How far is it away from the final value of the EMF? It is at a distance of EMF over E squared away from the final value. And if we went to t equals 3 tau, it would be EMF over E cubed away from the final value. So this shows that when the time increases by tau, the voltage gets closer to EMF by a factor of 1 over E. Okay, Giselle and Isabel, how would you like to go into the lab and build an LR circuit and do an experiment on it? Yes, that's what I thought you would say. So let's go and do that now. This afternoon, the three of us created the circuit shown here. We have two D-cell batteries connected in series. The positive end is connected to a switch. The other end of the switch is connected to a parallel combination of a solenoid, which is the inductor for our circuit, and a resistor, which I call resistor R1. And this parallel combination is connected to another resistor, resistor R2, which is connected to the negative terminal of the battery. Now, when I close the switch like this, I connect the parallel combination of the inductor and resistor R1 to the battery. And then when I open the switch like this, I disconnect them from the battery. In this experiment, we want to measure the potential difference across the inductor as a function of time when the switch is closed and then when it is opened. To do that, we have connected a voltage probe to the two ends of the inductor, and the voltage probe is connected to a lab quest, which is connected to the computer. Okay, so to do this experiment, Giselle, would you be the one to operate the switch? So you just close it and then open it. Oh, great. And Isabel, can we have you press the button on the mouse to start the data collection? Great. Okay, I think we're ready to begin. Oh, first of all, I need to zero the voltage probe at the beginning of the experiment. The voltage probe is now zeroed. Okay, we're ready to begin. Isabel, can you start the data collection, please? Thank you. Now, Giselle, close the switch and then open it. Great! The data is being collected. We are collecting 30,000 samples per second for 3 seconds. Here is a circuit which we constructed. In this circuit, R1 was 20.2 ohms, R2 was 20.3 ohms, and the EMF of the batteries was 2.80 volts. We don't know what L is. That's something we're going to measure later on in this presentation. I want you to make a prediction before we look at our results. Sketch a graph of measured voltage across the inductor versus time. Sketch it on axes like this. T1 is the time when the switch was closed. T2 is the time when the switch was opened. And let's assume that the time interval between T1 and T2 is large enough for the circuit to have reached steady state before the switch is opened. Spend a few moments to make your prediction. Oh, I'm going to give you a hint. Between 0 and T1, the voltage across the inductor is 0. So now take some time to make your prediction and draw your graph. Okay, you have time to make your prediction. Let's look at the experimental value which we found. Here we have potential difference across the inductor versus a time from 0 to 3 seconds. Our experiment took 3 seconds. Here's what we get. It is 0 at the beginning. Then we have a positive voltage spike. That's when the switch was closed. Then it falls to a non-zero value. It remains constant. Then we opened the switch and we had a negative voltage spike, and then it became 0. Let's look here when the switch was opened, when the switch was closed. Let's look up close at that point. Here's what we found. We had potential of 0, voltage spike going to 1.13 volts, and then an exponential decrease to 0.26 volts. In the last example, it went to 0 volts at the end. Why is it not going to 0 volts in this example? Giselle, can you tell us why? Very good, Giselle. Yes, the voltage does not decrease to 0 volts because the inductor also has resistance. And when we were in the lab, we measured that resistance to be 3.0 ohms. Good answer. Let's go back to our experimental data. Now, here's where we open the switch. Let's look at this area of the graph in more detail. So we open the switch. We had at the beginning 0.26 volts, and then there was a negative voltage spike. It went down to negative 1.72 volts, and then the magnitude decreased exponentially to 0. Let's look at the theory of this circuit after we open the switch. So there's our circuit. Let's say the switch has been closed for a long time, and then it is opened at t equals 0 seconds. So just before the switch was opened, there was current flowing up through the inductor like this. And then when we open the switch, that current starts to decrease. And so to oppose that decrease, the inductor is going to act like an EMF as shown here. The top part will be positive, the bottom part will be negative. And di by dt is less than 0. So the current is going to flow now up through the inductor and then down through resistor R1 like this. It won't go into resistor R2 or the battery. It's just going to go in a loop like this. So that's going to be the loop for the current. And di by dt is less than 0. And VL is negative L di by dt, and I've taken a negative sign here so that VL will be a positive number. Let's do Kirchhoff's loop rule. So let's start at the inductor and go around in a loop like this. So first we have VL for the inductor, and then a voltage drop as we go through the resistor of minus IR1, and that's going to equal 0. So let's put in what VL is. This is our VL. Put it into the equation, and we get our differential equation. Negative L di by dt minus IR1 equals 0. Now we need to solve this equation. What's the method to solve this equation? Separation of variables, just like before. So put all the i's on one side and all the t's on the other side. So first, let's write like this. Let's just rewrite it. Put IR on one on the other side. So L di by dt equals negative IR1. So let's divide by I and multiply by dt. And this is what we get. di over I equals negative R1 over L times dt. The variables have been separated. Now we can integrate. R1 and L are constant, so I take them out of the integral. This integral is just L and I. This integral is just t. So L and I equals negative R1 over LT plus C1, where C1 is a constant. We don't want L and I, we want I. So take e to both sides of the equation. E to the L and I equals e to the negative R1 over LT plus C1. I can rewrite this exponential into two factors. E to the C1 times e to the negative R1 over LT. This e to the C1 is just a constant. I'll call it C2. E to L and I is just I, so we get this. I equals C2 e to the negative R1 over L times T, where C2 is a constant. Now, we need to determine the constant C2. So what is our initial condition that we can use? Well, when t equals 0, I equals I0. So let's put these two things into this expression. So I is just going to be I0. T is going to be 0. This is what we get. I0 equals C2e to negative R1 over L times 0. Well, this is just e to the 0, which is 1. So we get I0 equals C2. And then we have our final result. I equals I0 times e to negative R1 over L times T. Now let's calculate the voltage. The inductor and resistor are connected together, right? So the bottom parts are connected together and the top parts are connected together. So they have the same voltage across them. VL equals VR1. There's two methods to calculate the voltage. Let's look at method 1. Here's the I. VL equals VR1. And VR1 is just I times R1. So multiply the I by R1. I0 e to negative R1 over LT times R1. And therefore we get VL is V0 e to negative R1 over L times T. Where V0 is I0 R1. That is the voltage across the inductor immediately after the switch is opened. Let's look at method 2. I is I0 times e to negative R1 over L times T. VL is negative L di by dt. So just differentiate this thing with respect to T. So negative L times I0. Differentiate this exponential with respect to negative R1 over LT. And we get e to negative R1 over LT. Then differentiate negative R1 over LT with respect to T. We're using the chain rule here. We get negative R1 over L. Look, the L's cancel out. The negative times the negative is a positive. So we get this, I0 R1 times e to negative R1 over LT. Therefore, we get this expression for VL, which is what we had using method 1, where V0 is I0 R1. Here is the measured values of V0 after the switch, VL, measured values of VL after the switch was opened. Now, I have adjusted the time for this graph. I put the time when the switch was opened to be t equals 0. And in this graph, we have V0 is negative 1.72 volts right down here. And it matches what we expect it to be. It's an exponential decrease of the magnitude of the potential difference to 0, like this. So measured VL matches the theory. We have curtains here because this is a very important and exciting question. Can we measure the inductance of the solenoid? The answer is yes. Here's what VL is, where V0 is negative 1.72 volts and R1 is 20.2 ohms. Now, let's divide by V0, and we get this. VL over V0 equals e to negative R1 over L times T. Let's take ln of both sides. So ln VL over V0 equals ln e to negative R1 over LT. Well, this thing is just negative R1 over L times T. So we have this. ln VL over V0 equals negative R1 over L times T. So we know what V0 is. We know what R1 is. We have measured VL as a function of T. So this is like a graph of, it's like this, y equals mx plus b. And in this example, we can take the y to be the ln, VL over V0. The x would be the t, and the slope, m, is negative R1 over L. And the b is 0. So we can create a linear graph. The vertical axis would be ln VL over V0. the horizontal axis would be t, and the slope would be negative r1 over L. Here's our data again. Now I'm going to use the first 40 points of this data. So from 0 to 0.0013 seconds. All of these points, that's what I'm going to use for the graph of the ln VL over V0. I'm not going to use this point because this gets very noisy here because it's fluctuating around 0 volts. Let's look at the graph which we got. So here I'm plotting ln V over V0 on the vertical axis, time on the horizontal axis, from 0 to 0.0013 seconds. Here's what we get. A very nice straight line. A bit more noisier at higher time. Let's do a best line fit. Here's our linear fit. Look at this. R squared is 0.9981. It's a very good fit. This 2969.9 or negative 2969.9 is the slope. So L is negative R1 over the slope. So it's negative 20.2 over negative 2969.9, and we get L is 6.80 millihenries. Are we missing something? Think carefully. Did we miss anything in our calculations? Isabel thinks we missed something. Yes, Isabel, you are correct. Can you tell us what we missed? Correct! The solenoid has a resistance of 3.0 ohms, which we did not include in our calculation. Now let's include the resistance of the solenoid. Resistance small r equals 3.0 ohms. This is our new circuit diagram. So I've replaced that inductor with an inductor in series with a resistor small r. And we measure the voltage across that combination of inductor and resistor of the inductor. So from here to here. Current is flowing upwards through the inductor and through that resistor R. And the current is decreasing, so the inductor needs to act like an EMF with positive up here, negative down here. Let's do Kirchhoff's loop rule. Let's go around like this, starting at the inductor. VL minus I small r, so that's the voltage drop across this resistor small r, minus IR1 equals 0. Then we get our differential equation. Negative L di by dt minus I R1 plus R equals 0. This is the same as the differential equation we had before, except R1 has been replaced by R1 plus R. So the solution is this. I equals I0 times e to negative R1 plus R over L times T. So the voltage that we measured is still the voltage across resistor R1 because we're measuring from here to here. So that's going to be IR1. So I0 R1 times this exponent. So it's the same as we had before, except instead of R1, we have R1 plus small r. So this is what we had before. L was negative R1 over slope. But now we have L equals negative R1 plus R over the slope. So negative 20.2 plus 3.0 over negative 2969.9, which gives us 7.81 millihenries. Here's a summary of what we measured for the inductance. For the LR circuit, not including R, we had 6.80 millihenries. For the LR circuit, including R, we had 7.81 millihenries. And for the LC circuit, which is in the video LC circuits, we had 7.33 millihenries. These are all for the same solenoid. And I encourage you to watch the video LC circuits. Here's a summary of what we learned today. An inductor acts as an EMF to oppose any change in current passing through it. For instance, here we have current to the right and increasing. So the inductor acts like an EMF in the direction opposite to that of the current to oppose a change in current. When the switch in this series LR circuit is closed, connecting the inductor to the battery, there is a sudden increase in voltage across the inductor. It goes from 0 to the battery EMF, and it then decreases exponentially to 0. So like this. Here's the voltage across the inductor. It's high and then goes to 0. Voltage across the resistor starts at 0 and then ends up at the battery EMF. In a real LR circuit, the inductor voltage does not decrease to 0 because of resistance in the inductor. So we close the switch, we got the voltage spike, then it decreased but didn't get to 0. It got to 0.26 volts because of the resistance of the inductor. Time constant, tau equals L over R. So when the time increases by tau, the voltage across the inductor gets closer to 0 by a factor of 1 over E. So starts at EMF, then at time tau, it's EMF over E. Time 2 tau, it's EMF over E squared. And we can assume that the system reaches steady state after a time of 5 tau. Voltage across the resistor increases from 0 to the EMF E. And when the time increases by tau, it gets closer to the EMF by a factor of 1 over E. So at 0, it's EMF away. At tau, it's EMF over E away. And at 2 tau, it's EMF over E squared away. When the switch in an LR circuit is opened, there's an initial negative voltage spike, followed by the voltage and current decreasing exponentially to 0. And here we have the measured voltage, which starts at negative 1.8, and then the magnitude of that voltage decreases exponentially to 0. And the inductance can be calculated from the measured inductor voltage as a function of time and the value of the resistor. So we had our plot of ln V over V0 versus time, and we found L was 6.80 millihenries. And we can more accurately determine the inductance by including the resistance of the inductor. So now we have the resistance of the inductor in our circuit. And we use R1 plus the inductor resistance, and we found L was 7.81 millihenries. Thank you very much for staying to the very end of this presentation. Giselle, Isabel, and I really appreciate your viewing of our presentations, and we enjoy making them for you. Please be sure to like and subscribe. See you next time. Bye.